Hello everybody and welcome back to my channel. In this video, we're going to redefine 5 significant dimensionless numbers used in fluid mechanics. The purpose of this video is to show that these quantities are not only ratios that anyone could have divided a long time ago and stick his name to. On the contrary, these ratios are the reason behind safety and low cost. I'd like to start with Reynolds number as it's the most used quantity, named after the British physicist Osborne Reynolds, who performed his elegant experiment in 1883. Reynolds brought to light the fact that going beyond a certain threshold deteriorates the nature of the flow. This threshold is a combination of parameters which make up his famous formula: density, velocity over dynamic viscosity of the fluid multiplied by the tube's inner diameter carrying this fluid, say d. That's in case of a circular tube, but is also applicable to other geometries. A common one is a flat plate, in which the plate length in the direction of the flow takes over the diameter. The threshold, technically called critical Reynolds number, varies from one shape to another. Values of common geometries are found in fluid mechanics textbooks. Any value of Reynolds number below the critical implies a smooth and regular flow, better known as laminar. Once this value is exceeded, a disturbed flow originates, representing a transitional phase dominated by a wavy flow. Beyond this phase, fluid particles move randomly, eddies develop, marking a turbulent regime. Another piece of information out of Reynolds number is what force dominates the flow. Is it viscous or inertial? Multiplying up and down by the velocity length, the numerator becomes an inertial force, while the denominator becomes a viscous force. When solving a fluid mechanics problem, we use Reynolds number to determine whether the flow is laminar or turbulent, also to perceive how the inertial force compares to the viscous one. Why is it important? Imagine life without Reynolds number, then this huge aircraft must be completely built to test its aerodynamics, something extremely impractical and certainly wastes tons of money. Thanks to Reynolds, a scaled-down model could be built and stationed inside a wind tunnel, which carries the same Reynolds value of real flight conditions, with the flow properties and modal dimensions brought down to a certain scale, simulating how a real large-scale aircraft will perform during takeoff, landing, and other flight conditions. Mach number. Named in honor of Ernest Mach, an Austrian scientist born in Brno-Hrlice, Czech Republic, this quantity is expressed by the ratio of the object's speed to that of sound in the medium, and it's crucial for identifying flight regimes and compressibility effects ranging from subsonic to hypersonic. Why do we need it? Because the aerodynamic behavior changes when surpassing the speed of sound, and since the speed of sound varies with altitude, so does the speed at which the object reaches supersonic state. So a wind tunnel is necessary for studying a scaled-down model to predict how its larger exemplar would behave at different Mach numbers and verify it's valid and safe for flying or must undergo design adjustments. Froude number. In the past, everyone thought small models are just for fun until an eminent English engineer named William Froude built his own facility called a towing tank, something like a large basin where the model is towed by a carriage to be tested before approving a larger prototype. By using his dimensionless quantity being equal for both model and prototype, he was able to lower the velocity of the model in the towing tank along with its length and predict precisely the behavior of the larger prototype. This technique is still used today by giant chip manufacturers despite all the advanced computer capabilities. Thanks to Froude, chip manufacturers can rely on his dimensionless number instead of building 20 chips before verifying which one suits best. Strouhal number. This dimensionless number was a great contribution to fluid mechanics, named after the Czech physicist Zdeněk Strouhal, who in 1878 discovered this number while performing his experiment with wires experiencing vortex shedding. Strouhal number combines the frequency of vortex shedding, flow velocity, and diameter. Large values reflect the domination of oscillatory flows. Low values imply oscillations are swept by rapid fluid motion. It's widely accounted for in construction of buildings and bridges to help prevent vortex shedding, which could lead to structural failure. You might find the Strouhal number denoted as SR in order not to confuse it with another dimensionless number called Stanton number. Weber number. This ratio is named after Moritz Weber, a German engineer famous for his works in similarity and two-phase flow. This ratio shows how important is the inertial force to surface tension. The Weber number is crucial when analyzing the formation of bubbles and droplets. Besides inertia and viscosity, surface tension plays a key role in inkjet printing. To ensure stable printing, for example, the ink used must be confined to the printable region determined by the printing indicator ranging from 1 to 10. Therefore, in order to prevent splashing and other printing problems, the Weber number must always be satisfied whenever a change in parameters is encountered. So that's all. I hope this was helpful. Please don't forget to like and subscribe. Thank you very much for watching and see you